Okay, so hello everyone. In this video, we will be discussing basically the Haigen poiselle flow, which is a flow of liquid through a circular pipe of certain given radius and length. So firstly, we will be looking into the shear stress distribution and then move into the velocity distribution, how the velocity is varying over the pipe with the different y, what are the velocities, and then we will be deriving the head loss equation and the pressure drop along the length of the pipe. So let's begin. So first of all, in this case, the pipe is fixed. That is, both the top and bottom walls of the pipes are fixed. So these are the two surfaces of the pipes which are fixed. And we will be considering our axis like this, and from here at a distance r, we will be selecting one small elemental strip of radius r and length dx, and the total radius of the pipe is capital R. And let's assume that the length of the pipe is capital L. So for our analysis purpose, we have considered one small elemental strip of radius r and length dx. So on this elemental strip, we will be first calculating the shear stress that is acting on the strip. So if you take out this small elemental strip, then you can observe that pressures are acting on both the sides, this side and this side. On this side, the pressure is Px into cross-sectional area of this, that is, let's suppose pi small r square, and since this length is dx, so here the pressure will be Px plus dou p by dou x dx, and the cross-sectional area is same, pi r square. This comes because due to the here the pressure is Px. So if you move at a distance x, if you are moving, the pressure is going to increase. So we will be getting some pressure Px plus some small increase in pressure. This small increase in pressure can be accounted because if the pressure is increasing, if the pressure here is small and the pressure here is large, then only the flow will take place. The flow of fluid always takes place from higher pressure to lower pressure. Alright. So after this, the pressures are acting on both the sides, and some shear stress will also be coming, that is tau into circumferential area. The circumferential area will be 2 pi r into dx length. So 2 pi r, that is this circumferential direction, that is 2 pi r into dx length. So this is the circumferential area, this is the area of this place, and this is the area of this place. Alright, so here, since the fluid is not at all accelerating, we are assuming the flow to be steady flow and incompressible flow, and the flow is also fully developed flow. So because of all this reason, the acceleration in the x direction, I am assuming that this is our x direction and this is our y direction. So acceleration in the x direction is 0. You can also get this acceleration value from the acceleration formula, which is acceleration. I am just giving you a rough idea how the acceleration in the x direction is 0. So acceleration in the x direction will be du by dt, total derivative of the velocity along the x direction by dt. So if you open up this formula, you will be getting dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z. I assume that you already know what are u, v and w. So u, v and w are the velocities along the x, y and z directions. So since we are assuming the flow to be steady flow, so there will be no change in velocity with time. So this will be 0. Since the flow is steady flow, since the flow is fully developed flow, because of fully developed flow, there will be no variation of the velocity along the flow direction, that is along the x direction. So dou u by dou x will be 0. And since we are considering the flow to be only in one direction, so the velocities of the fluid particle along the y and z direction respectively will also be 0. As a result of this, v and w will be 0. So if v and w are 0, these two will also be 0, and 0 plus 0, everything is 0. So acceleration in the x direction will be 0. Alright, so from Newton's second law, what we know that summation fx will be equal to mass into acceleration along the x direction. But since acceleration is 0, so this one will also be 0. Now, what are the forces that is acting along the x direction? So this is in positive x, this is in negative x, and this is also in negative x. So we will just put the values here, px into, I am writing pi r square as area, capital A, will be balanced by px area plus dou p by dou x dx into area, and plus 2 pi r tau dx, right? So this and this one will cancel out each other, and if you further solve it, that is dou p by dou x minus of dou p by dou x dx into area, dx into area will be equal to 2 pi r into tau dx. So dx and dx will cancel out each other, and what is the area here? The area here is pi small r square, right? So pi small r square. So pi and pi will cancel out each other. 1r and 1r will also cancel out each other. So from here we get the shear stress is r by 2 negative dou p by dou x. So from this equation we can observe how the shear stress is varying with the r direction or with the y direction, that is radially how the shear stress is varying. So radially you can observe that shear stress is varying linearly, since r to the power 1, so it's varying linearly. So at where the maximum and minimum values of tau will occur, the maximum value of tau will occur at the surface, at the walls, which is at a distance of capital R. So we will be having r by 2 minus dou p by dou x. This is the maximum value of shear stress, and where the minimum value of shear stress will occur, the minimum value of shear stress will occur at the center line where r is 0. So the minimum value of shear stress will be 0, that is where r equal to 0. So these are the two upper and lower limits of the shear stress. And if you want to observe how the shear stress variation takes place over a particular cross section, then you simply draw the cross section over here if we are interested to observe how the shear stress is varying. So here the shear stress is 0, and here the shear stress is maximum up to some extent here. So from here to here it is varying linearly. So just join these 2 points linearly, and this will be your shear stress variation, right? And this equation can be given as tau equal to r by 2 negative dou p by dou x, right? Okay, so after this we will be moving into, this is complete shear stress distribution. Now after this we will be moving into the velocity distribution, how the velocity is going to vary, because as you can observe, the velocity at this point will be obviously greater than this point, because we are assuming no slip condition. So the velocity of the fluid particle that is present on the walls will be 0, and because of viscous effects, so the velocity will keep on increasing as we move closer to the center line. Because of the viscous effects, the fluid particles that are present over the wall will try to slow down the speed of the particles above it due to momentum transfer, and as a result of which the velocity will not be constant at any particular cross section. It will be varying somewhat linearly, logarithmically, or exponentially. We have to observe that. So So now for the velocity distribution, we will be taking again the circular pipe of radius capital R, but this time we will be selecting the element from the wall. We will be taking the distance instead of earlier what we did. We choose the center line, and from the center line we choose one element at radial distance R, and we performed our analysis on this element of right. But this time we will be selecting, this is our center line, we will be selecting the element from a distance y from the wall. So here we have our element whose radius is smaller, and this capital R is the radius of the circular pipe, right? So if this is R, this will also be R. So if you write that R equal to, R can be written as small y plus small r, right? Small y plus small r. Now if you differentiate it once, if you differentiate this equation once with respect to R, let's say, then you will be getting that capital R is constant. It is the radius of the circular pipe, so it will not vary, so it is 0, and this one will be dy plus dr. So you can say that dy is equals to negative of dr. So now let's begin our analysis. So for finding the velocity distribution, what we will be writing the shear stress equation at this y distance, right? So tau, shear stress, from Newton's law of viscosity, we know tau is equals to mu du by dy, and this dy is taken from the wall. So what is dy? Dy is minus of dr. So just substitute the value mu into du by dr of negative, right? And from the earlier case, what we observed, that tau at any general location r, small r, can be written as r by 2 minus dou p by dou x, right? Just substitute the equation over here, that we will be getting small r by 2 minus dou p by dou x will be equal to minus mu du by dr. So we have to rearrange the terms and then we will integrate. So keep du one side and dr and r, all the other terms that side. So what you will be getting, du is equal to 1 by twice of mu negative of dou p by dou x, and here we have r dr, and integrate both the sides from 0 to capital R, and here from 0 to u. U is the maximum velocity of the fluid particle at the center line, right? Or let's say if you want to find the general expression, then instead of capital R, just write some within limits like 0 to small r, like from here to here you are finding the velocity at this point. So for that 0 to u and 0 to small r. So integrate u, and here we will be getting 1 by twice of mu minus dou p by dou x, and here you will be getting r square by 2, right? And here I am writing the limits. So we have u equal to 1 by 4 mu minus dou p by dou x, and here we have r square. So this is the expression for velocity at any local distance small r. So from here we can say that the maximum velocity u max will be equal to minus 1 by r square by 4 mu minus dou p by dou x, because at r equal to capital R we will be having the maximum velocity, and it is observed that small r equal to capital R, we are getting the maximum velocity. And what is the minimum velocity? The minimum velocity is of the walls, which is equal to 0. So minimum velocity will be equal to 0 at r equal to 0, right? So these are the values, and if you observe how the velocity is varying with radius, the velocity is varying with the radius parabolically. So because r to the power 2, we have some equation r to the power 2, so the velocity, local velocity is varying parabolically with the radial distance. So if you want to observe the velocity distribution at any particular section, here the velocity is 0 and here the velocity is maximum at this point. So if you join these 2 points, it will vary somewhat like this. This is a okay. So this one is a parabolic variation from which is governed by the equation small r square by 4 mu negative dou p by dou x. Right, so these are the velocity variations and shear stress variation that we have observed. So at the center line the velocity is maximum, and as we move towards the wall the velocity decreases and eventually becomes 0. And at the center line the maximum velocity is capital R square by 4 mu negative dou p by dou x. Okay, so these are the velocity and shear stress distribution, and now we will be looking into the head loss and how the pressure is going to vary as we move along the flow. Because as you are moving from this point to this point, the pressure is obviously going to vary, because without the pressure, without any change in pressure, there won't be any flow taking place. So the pressure have to increase or decrease, let's suppose for now, as we move towards x. So how the pressure is varying, we will be looking into it. Now for the pressure variation, we have the equation. So we have the equation of velocity distribution, where u equal to we have the velocity distribution u max, maximum velocity will be r square by 4 mu negative dou p by dou x negative, and this was the equation. So we have u max will be equal to r square by 4 mu, and this will become delta p and total x. I am considering that the dou p by dou x we are considering for the whole. So for the whole, like from this point to this point, let's say here the pressure is P1, here the pressure is P2. So as we move from this point to this point, dou p will be changing pressure, that is P1 minus P2, right? P1 minus P2, since the flow is taking place from high pressure to low pressure, so P1 will be greater than P2. So we are taking delta P as P1 minus P2, and the distance between these two pressure points will be L. I am considering, so delta P by L simply. And we have the expression for average velocity and maximum velocity. We have one relation for Haigen poiselle flow. The average velocity is half of maximum velocity. This expression we actually get it from the discharge formula. Like we have the discharge Q. For any general flow, we have the discharge Q, or you can directly find the average velocity by 2 by r square integration 0 to capital R ur dr, right? So if you substitute the general expression of velocity here and then integrate with the limit 0 to r, then solve, then you will be getting that the average velocity is half of maximum velocity. So we will be just taking help of this expression and substitute here. Instead of u max, we will be writing twice of velocity will be written as r square by 4 mu and delta p by L. So from this, if you find the expression of delta p, you will be getting 8 mu VL divided by r square. Now instead of r square, we always write in terms of diameter of the pipe, because whenever you go to the market, you purchase pipes with diameter specification. You don't say that we need a pipe of radius 10 cm or 20 cm. We always try to mention the diameter or thickness of the pipes. So for that, substitute diameter in place of radius. You will be getting 32 mu VL divided by d square. So this is the pressure drop as you move along the x direction. So from here we can observe one interesting point, that the pressure drop is inversely proportional to the diameter of the pipe. So as the diameter of the pipe increases, the pressure drop decreases, right? As the diameter increases, the pressure drop decreases. This can also be validated from the Bernoulli's equation, but from the Bernoulli's equation, like as the area increases, the pressure decreases, because the area increases, the velocity decreases, so the pressure decreases, right? So as you keep on decreasing the diameter, the pressure increases. And similarly for the average velocity, and then as you keep on increasing the average velocity, the pressure drop increases, right? So from the pressure drop equation, we can easily find the head loss. What is the head loss? That is governed by rho g into HL. So HL is the head loss, so HL can be written as 32 mu VL divided by rho g into d square. So these are some terms of head loss and pressure with which are relating with the average velocity. But if you are interested in finding the pressure loss and head loss in terms of these charts, then you can simply substitute Q equal to pi by 4 d square into velocity, average velocity. So V will be equal to 4Q by pi d square, and just substitute that V here in this two equation, then you will be getting the head loss to be 128 mu QL divided by your d to the power 4. D to the rho g d to the power 4. So these are some expressions. Now from the Darcy-Weisbach equation, if you equate this term 128 mu QL divided by rho d to the power 4g with FLB square by 2gd, then from this you can also find the expression for Darcy-Weisbach coefficient, friction factor, which is 64 by Reynolds number. So in case of laminar fully developed flow through a circular pipe, the conclusion is that the flow depends only on this parameter, that is the friction factor depends only on Reynolds number, and it is independent of anything. And the head loss, if you observe, it is dependent on these terms, like how the losses are going to take place when the fluid is going to flow over this circular pipe of radius r. What are the losses and how much is the loss going to take place, we can calculate from this formula. So that's all for this video. And if we want to summarize all the terms, we can observe, we can remember some key points, like first the shear stress varies linearly with the radial direction, then the velocity varies parabolically with the radial direction, and the head loss and pressure loss are this and this, like 32 mu VL by d square, and the head loss is 32 mu VL by rho g d square. And in case of laminar fully developed flow through a circular pipe, the friction factor is only dependent on Reynolds number. That's all. Thank you.